day everyone, welcome to my YouTube channel today, Science with Analogous. Where we talk about chemistry, biology and biochemistry in general. Alright, today we are going to be diving into this video quickly. It's how to calculate oxidation number. Now this is a subtopic in redox reaction. There's no way you can balance redox reaction, or there's no way you can observe if a reaction is redox if you don't know the concept of oxidation number calculation. Now, how to calculate oxidation number? Now, before you calculate any oxidation number of any element or any species, let's say we have LiAlH4. Now, we want to calculate the oxidation state of aluminium, or in a case where I have as very popular KMnO4, I want to calculate the oxidation state of manganese. Now, how does this thing go? Now, there are some rules we follow, some basic rules we are going to follow in order to get the oxidation number of any of the elements in this compound. Now, quickly, the rules are one. So the oxidation number or the oxidation state of a neutral compound or species is 0. What do I mean? Now, like this compound now is neutral. Why is it neutral? In the sense that it has no charge. Now, assuming it was LiAl, let's say 4 plus or 4 minus, this species is no longer neutral, it becomes ionic or charged. That's that. Now, for this neutral species, the oxidation number is equal to 0. So, if I take it, the total oxidation number of this compound will be equal to 0. Rule 1. Rule 2. The oxidation state of an ion or charged species equals the charge it is carrying. I already established that. Now, quickly, let's say I have NO3 minus. What is the total oxidation state of this species or compound? It's going to be -1 because it carries a -1 charge. Or another case where I can have a species like this, let's say MnO4 minus. What is the oxidation state of this species? It's equals to -1. That's the sum oxidation state of this species because the charge it is carrying is a -1. Now, that being clear, going to the third rule. Say the oxidation state of hydrogen is +1, but -1 in hydride or hydrido. Now, what do we mean? Assuming I have a compound like LiAlH4. Now, we already established that this compound is not charged. That means the oxidation number will be 0. Some oxidation number for the compound will be 0. But what we are saying now is that the oxidation state of hydrogen in this compound would be a -1. So the lithium should have one oxidation state. Maybe we are looking for aluminium, but for hydrogen it's going to be -1, and there are 4 hydrogens here. So -1 times 4. So that is hydrogen's portion in this compound. Now, moving on to the third rule. Now, this for an hydride, though, for an hydride. Now, how do you make a compound is an hydride? You can observe if a compound is an hydride or an hydrido if hydrogen is ending the compound. But if the compound is not an hydride, the oxidation state from the rule is +1. Let's say I have H2SO4. Now, very common strong acid. What is the oxidation state of hydrogen in H2SO4? It's going to be +1. Why? Because hydrogen is not ending the compound. In this case, hydrogen is more like starting the compound. So the oxidation state of hydrogen will be +1, and there are 2 of it, times 2. Maybe we are asked to look for sulfur. Then we can have that of oxygen. Then everything should be equal to 0 because the compound is not charged. Now, moving on to the fourth rule at this corner of my board. Now, it says the oxidation number of oxygen in compounds is -2. So, in this case, if you have to look at this case, the oxidation number of this oxygen should be -2. And looking closely, there are 4 oxygen there. So it should be -2 times 4. Now, with this expression on the board, I can therefore calculate the oxidation state of X, which is sulfur. Now, rule number 4 is not complete, not completed for a reason. Now, the oxidation number of oxygen compound is -2, except in, now there are compounds we call peroxide. Peroxide. What is a peroxide? A peroxide is a compound that have an extra oxygen, or an oxide with an extra oxygen. Let's say common oxide, like let's use the likes of CaO, that is calcium oxide. Giving it an extra oxygen should make it calcium peroxide. Let's take another one like sodium oxide. Giving it an extra oxygen should make it sodium peroxide. Now, let's say we don't know this, or let's say this is too complex, or let's say it's too basic for some of us. Now, peroxide usually have this ion present in them. They have O22 minus, or we say they have extra oxygen linkage. Popular example for water. What is the oxidation state of hydrogen in water? Hydrogen is +1 from our rule because hydrogen is starting it. Oxygen is -2 because oxygen in compound is -2. Now, quickly, we can quickly say that the oxidation state of the whole compound is 0. But how do we change this thing from this oxide? Why do you change this oxide to a peroxide? It's just adding 1 oxygen. So adding 1 oxygen like this can make it H2O2. That becomes hydrogen peroxide instead of the hydrogen oxide, which we call water. So this is the oxide, this is the peroxide, extra oxygen. And rule number 4 says oxygen in compound is -2. So this normal compound we know, normal oxides we know, oxygen is -2. But in the case of peroxide, where you have an extra oxygen, oxygen becomes -1. So in this peroxide, the oxidation state of oxygen is -1. Are we there? Now, since we are following -1, there are other higher cases, like where we call the superoxide. So I can add to the rule, except in peroxide, where it is -1, and superoxide. Yes, superoxide. Where it is -1/2. That means the oxidation state of oxygen in superoxide is a -1/2. How? Now I'll show you what is superoxide. Superoxides are oxides that have higher proportion of oxygen than peroxides. Now I have, for instance, I have K2O. This is potassium oxide. How did I get potassium oxide? The addition number of potassium, I'm coming there, is +1. The addition number of oxygen is -2. So let's take the valency as 1, a +1. So this is a +1, this is a -2. Removing the charges, that becomes the valency. So I can exchange and write a compound. So I should have K2O1. So that's potassium oxide. Now adding one extra oxygen makes here K2O2. That is potassium peroxide. Potassium peroxide. Now potassium peroxide, I can also rewrite it as KO. Because empirically, I can just say 2 here 1, another 2 here 1. So I have K1O1. So potassium peroxide can be KO. Now what I'm saying is that adding an extra proportion, or adding 1 proportion of oxygen or more proportion of oxygen, as the case may be, to an oxide, usually oxides of metal, adding an extra oxygen to their molecular fraction will give me a superoxide. So the superoxide of potassium should now be KO2. And it should be noted, only very reactive metals can form superoxides. The likes of potassium, the likes of barium, the likes of rubidium, the likes of cesium. Only these metals can form superoxide. Moderately reactive metals like magnesium, aluminium tend not to form superoxides. That is a superoxide. And the superoxide, the oxidation state of oxygen is -1/2. Having known these rules, there are some basic rules again we have to know. Group 1 metals, namely sodium, lithium, potassium, and rubidium, usually have oxidation state in compound to be +1. Group 2 metals such as calcium, magnesium, beryllium, strontium, and coal usually have oxidation state in compound to be +2. So we have oxidation state of group 1 metals in compound to be +1, group 2 metals in compound to be +2. So with these rules on the board, and with these rules I've been explaining, you can calculate the oxidation state of any element in a compound or in any species. Now I will take 1 or 2 examples to illustrate what I've done. Now I'm going to put those examples somewhere here. Now I'm going to work with it. Now I'm going to use this example of, let's say, H2CrO2O7. Yes, dichromic acid. Now, dichromic acid on the board is H2CrO2O7. Now, they can ask us to calculate the oxidation state of chromium, CrO. Because the oxidation state of hydrogen and oxygen are well present and illustrated in the rules. Now, quickly, since it's a neutral compound, the oxidation state will be 0. Now, what is hydrogen? Hydrogen is going to be +1 because the oxidation state of hydrogen in the compound is +1, except in hydride or hydrido. What is an hydride? When hydrogen is any the compound, these are hydrides. It's an hydrido. Now, so +1. How many hydrogens are there? 2. Plus. Now I have chromium. There are 2 chromium. Let's say chromium is H. You are looking for it. 2 of it, X. 2X. Now, what is oxygen? The oxidation state of oxygen is a -2 times 7, because there are 7 of it. Oxidation state of oxygen is -2 in compound, except in peroxide. Most compounds are usually in the oxide form. Most combination of oxygen are in the oxide form. Times oxygen tends to be divalent in them, except in very special cases. Yes, and those special cases are illustrated or can be visible, can be observed very fast. Now, here oxygen is -2. Total, everything is equal to 0 because there was no charge. So quickly, now this is going to be 2 plus 1 times 2 is 2, or +2, plus 2x plus -14 equals 0. So -2 times 7 is -14. And from your simple mathematics board mass rule, minus plus should give me a minus. So I should take here to be -14 equals 0. So what does it mean? What do we mean by this? Now, how do we find X, which is for chromium? So quickly, I can say 2x is equal to, now this is a +2, so -14 is going to cross, so it turns to +14. Now, +2 is going to cross to -2. By the end of the day, I'm going to have, pardon me, let me just use this whole side of the board. So I'm going to have, at the end of the day, I'm going to have 2x is equals to +10. 2x is equals to +10. So +14 -2, that's a +10. It's equals to +10. So at the end of the day, I'm going to have, check, So minus 2 times, sorry, pardon me, minus 14 minus 2 is plus 12. That was a mistake, a beautiful mistake. Now, because this is minus 4, this is plus 14, you remove 2, that's plus 12. So we're going to divide both sides through by x. Now, dividing by x should be, or I said divided by x, divided by 2, pardon. Divide both sides by 2. Simple, so take 2, take 2. So 2 here gives me 6. So that means x is equals to plus 6. So the oxidation state of chromium in H2 CrO2O7 is plus 6. Dichromic acid. So I can call this thing, or I can call this compound eta-oxo-dichromate 6 acid. That's for the impact nomenclature. Come again. Eta-oxo-dichromate 6 acid. So even in the impact nomenclature of inorganic compounds, the oxidation state is still very, very valid. Now, one more example. So you can go to your books and quickly check out. You can go to your book and read one more example. I'm going to do for MnO4 minus. That is charge special. So quickly, the total oxidation state is equals to -1. I believe there's no contradiction because it is an ion. The charge of an ion is equal to the oxidation state of the whole ion. So the question will always ask us to calculate Mn, calculate the oxidation state of Mn in MnO4 minus. So quickly, we already know that oxygen is usually -2 in compounds. So we're looking for Mn, which is x plus, quickly, plus -2 times 4. There are 4 oxygens. By the end of the day, I have x plus -8 equals -1. So quickly, so it's now be x minus 8 equals -1. Because the plus, so at the end of the day, I'm going to have x is equal to -1, -8, cross over the equal to sign, plus 8, and that should be plus 7. So this ion is going to be called tetraoxomanganate 7 ion. Let me write it down for you so that you get it. So it's usually involved in the impact. So tetraoxomanganate 7 ion. So this is the impact name of the ion of the special. So with this point of mind, I believe everybody can go through this rule and solve more questions, because you need to know this before we balance redox equation. The next video will be balancing redox reaction. So for now, it is a goodbye. So have a nice day, everyone. God bless you.